Okay, at this point, I hope you downloaded all the files, and let's launch Fluent. So my advice, you have the workbench now, so you can launch the workbench or the standalone version of Fluent. My advice is to use the standalone version, okay? So I will launch a standalone version of Fluent. So remember to put here your working directory. Whatever you extract those files, you will put it here. Number of processors, 3D and double precision. I don't see any reason not to use double precision. Okay, the only thing here is that you will consume more memory, but you might get that a little bit extra accuracy. Okay, so just launch standalone. I already have it here, and in our workflow, in our cases that we have, let's first run the quartz runs. Okay, so this is the clean case. We just have there the case at top. So I will open cases, my runs case. Okay, so we have the mesh. Okay, reading here everything has been set up for you. Okay, even the boundary condition, the periodic one. Probably in a later tutorial will show you how to set up this mesh, all the conditions if you want to use the file, the automatic setup file. So we have this, everything defined. So look at that, the mesh is a perfect mesh. So remember when we were addressing the theory, I mentioned that this kind of scale resolving methods, they rely on very good meshes, very good quality meshes, and it's either cells. So the only thing that you can see here that it seems to be a little bit this stretching here, a little bit, the cell seems to be a little bit large. We're going to see how to set the quality, but it's true, and this is why we are not resolving well the stretch. In the fine mesh, it is divided by 2, this one, so you can resolve better. So let's explore here our workflow. So we go general, steady will be the first solution. The method, feel free to choose any method. I will choose the standard 1K omega SST with production limiter, okay? Nothing else to define here. Materials, remember that we're using water liquid. As you go back to the slides, so I should have, let me go back here, and so in the description here, you have the working fluid, water, okay? So, and the values of velocity that you need. So you will need to adjust that a little bit. So I have done everything already for you. So as you go water liquid, so you put density and the viscosity level value. Okay, everything compressible. So boundary conditions. Then let's explore here. So we have an inlet. So we have the value as the one defined, okay, in the description, but also the experiment. As you go back to the page here, you will go probably these two papers, the two first, that you have all the information as experiment, and these values also, you know how to choose this one, but if I would recall, I chose this one just to reproduce the experiment. Nothing else to do here. Then we have the outlet. It's just a simple pressure outlet. Top and bottom, remember that these are walls, but they are slit walls. So as you go here to define a slit wall, you go here, specify shear, and put it 0, 0, 0, and means that you have there, you have no boundary layer there. So we also in the theory address this, the roughness, and if you want later you can run and see the influence of roughness. Then we have the square, which is another wall, but in this one, yes, it is no slip. So see that we have no slip defined, and then you will have the back and front, these two page surface boundaries. In this case, we already created, so we collapse those two surfaces. And here also is important, you see translational periodicity, and also we have the boundary conditions. And it's important here that you need to define here the flow direction in this when you in this boundary condition. So here we have the flow, the periodicity in this direction, you define it there. Okay, so nothing to define pressure gradient 0, so this will have no influence there. So we keep moving. We have this reference values, so you have the reference values to compute all your forces, everything. And it's important sometimes some people use the turbulence intensity just to make it clear. So here we're computing all the forces, but also if you were not computing forces, you will need to set this velocity value just for the turbulence intensity. Remember that turbulence intensity, you get the RMS divided the string free stream values. This is the value you get to compute that, and some other quantities that are normalized. But in any case, these are the values to compute forces and everything, and pressure coefficients and so on. So let's go for method, and the first method that we're going to use is the couple. So we're going to play with two methods. Okay, we're going to use the couple, the fully coupled, and then the segregated solvers. So we have a numerics that is second order. We say that this method for a steady simulation is the best method. It might be a little bit expensive from the point of view of the computational effort, but it will converge very fast to steady solutions. We're going to see that in here. Methods, nothing to set up here, and controls. Okay, then we go report definitions. Remember to set up all your reports. So here steady, we just are computing initially CD, CL, lift and drag, and Y plus. I put here just Y plus maximum, but also you will need to compute Y plus average. So let me show you how to add that monitor also. So you go into surface, facet average. So you want to compute that only in the square. Let me call it Y plus average. And I want just report to plot, and that's all. Everything okay. And you have it there, okay? So we have the two monitors. Residuals, let's use these values are okay. Then report files are saving all this information to output files. So in your working directory, in this case, we open everything here, runs. We're going to have all these files there in your working directory. So every output file, you will have it there. The plots, we are going to add a converge condition. Okay, so we're monitoring CD. We have work in this. So when CD is not oscillating anymore, it will stop. Self register, we have seen that we can use this one for adaptive mesh refinement. We're not going to do anything of that. And then we go initialization. Okay, so we compute values. Okay, from inlet. So meaning that I'm using the values that I given at the inlet to initialize everything. So you press initialization, and now we have initial conditions. Okay, so remember every now and then save. So I will put here, and I will call the first one couple, and we have that already a case ready to run. See that also, so you go graphics, I already created also a few cut planes. Here you have lines where we can do sampling, velocity, probes. So when we move to SRS, we need this probe to save velocity, and then you want to plot the turbulence spectrum and everything. And here are some planes, so we can already have been predefined. Something interesting, important that also is you go to here in parameters and customization, custom field. I already predefined this one. Also these two functions. We saw that in the theory also L0, which is integral length and scale. So record for the slides, the lectures that we computed like this. And then we have RL, the refinement ratio. This one is the one that is going to tell if we are solving that turbulence spectrum. Okay, is the mesh is good enough to resolve the integral length scales. So we have that defined. If you want to define something else, also feel free to add it. So having this, let's run this case. Okay, before running also, okay, let me plot here. So see that we have a uniform solution. Okay, now I want to see this one, velocity, outer range. We have a uniform solution. And I want to use the full multi-grid initialization. Remember, initialization is very important. If you put in good initialization, you are going to converge faster. Okay, so let me run with the uniform solution, and then we do the non-uniform. But for you, just go right ahead and use the full multi-grid solution. Okay, let me run here. It might be a little bit fast, and let's see how long it takes. So see that, okay, it's just launching all your quantities that you're monitoring. And well, I make a mistake here. I didn't put the monitor for the Y plus. I left it for the average pressure. So let me stop here and fix that. Just to show you also that doesn't require you to start from scratch. So you can go here and report definition. It was this one. So I forgot to define here turbulence, and it should be Y plus or Y star, is up to you. So you can check compute. Okay. Okay, so now it has been updated. And let's wait a little bit, okay, and see the output. Okay, so the simulation arrives to a converged solution. So see that both monitors converge. My residuals on the monitor that we put in CD, and it arrived very fast, relatively in about 8 iterations. It arrived to the converged solution. So you can explore here your Y plus maximum is something about 30. You have the average also. Okay, I took data. I didn't update it. Then we have leave drag all your signals here. Okay, the forces and the coefficients. So let's rerun the case. But now let's use the non-uniform solution. Okay, so before also let's visualize a little bit the solution. So see that this is the solution we have. Actually, I arrived to a converged solution. And what is interesting, look at what is happening here. That here we know that we have a weight here, the onset of a weight, but the solver is just not predicting that. Okay, the coupled solver is arriving to this solution. This doesn't mean it is wrong, it is right, but it is a solution. Okay, so let's change now and let's rerun, but using non-uniform initialization, the full multi-grid. So let me initialize again. Okay, so we go to 0. By the way, see that here we have state wall. So in the initialization, probably you will see here that you have boundary layer, but then when it runs, you don't have that effect anymore. So remember that you go to solve in your text user interface, then initialization, and we use here FNG. Okay, yes, and it will run a fast, let's say initialization there, iterate fast, and now if I go here, we have this is initialization. Okay, so this is much better than a non-uniform initialization. Let me fix the problem with the report definition. Report plops should be this one. So here, okay, I should have the average value, this one. Okay, so you can update it like this. So if you want to add something else to that plot, so let me add also Y plus maximum. Sorry, I have it there. So these two, I'm plotting those in the same plot. Okay, so let me launch again. Okay, so remember previously it was about 8 iteration. Now we have this initialization. Let's see if we get any speed up. So we have some output files. It's just asking you that if you want to create new files, if you don't want to overwrite whatever you have in that folder. So see that in your working folder, you have the output text file. So you can use a decent text processor editor. So I use this one, Sublime Text, which is free in Windows. And you have your files there. So let's say that I want to no, because I want to overwrite, yes. And now it will overwrite. So starting from that condition, it will start to iterate, and see that here we are plotting the two. So you have maximum and the average. So let's see how many iterations takes in this case now. Okay, in my case, I arrived to a converge solution. So see that now it was both monitors arrived to a converge about 74, which is faster. You can see that it's faster than the previous one. Might not be not much, but in some cases will be, you will feel the difference. Okay, so see that we have all the monitors. Okay, so we have Y plus average. Maximum is about 30, the average, let's say about 10. Probably it's not the desirable value, but we know both functions, they do a good treatment. And your coefficients, everything here. And let's take a look again at the new solution. Pretty much the same, okay? So we didn't have much an influence in your final solution, in the, let's say, qualitative solution, but in your converge rate, it was a difference. So we have that one, we play around with this solver, and let's save this one again, we call it couple. And now just to remind you how to save the interpolation file. So see that we have file, interpolation, and you go here and you can write in this cell zones, because you can have more complicated cases, you can have different cell zones, and you would like to save everything there. And you give it a name that we call it couple, okay, because now we're going to run using another solver, and we save the file. Okay, so as you go to your working case, you will see here that you have your interpolation file. So see that everything that you're doing is being saved in your working directory. So now this interpolation file can be used as a starting condition to another to work in another different mesh or different case using the same mesh. So now let's do something. Let's again initialize, zero initialization, and let's do the only modification that we are going to do is just changing the solver. Okay, so recall that this one is converging like in 70 iteration very fast, and let's go to the simple solver. Okay, this is the other family, these are the segregated solvers. So, and let's use the default parameters. Okay, so you go here, everything is alive. So just to make things faster, if we already have a previous solution, okay, why not using that? So just to use that previous solution, you go into interpolate, read and interpolate, and I want to read that data that we just saved. You see here, read, and the data was interpolated, and we have that solution to use in our new solver. So this one, in this case, we did it in the same mesh. You can do it with different meshes, even different domains. It will interpolate where you have cells that are matching, where it is possible to pass the solution. So we have we have this, and we can run. But before running, let's do something else just to show you. Remember that also that we have initialization an option that we can perturbate the field. Okay, so let's do something. And let me see when you go into solve initialize, you have this, and you can add perturbations to your initialization. So as you go in turbo, okay, that will add fluctuations. And basically this is what you have now. So this is even better because you have a fluctuation that can have an influence in your solution. So let's do something that before running the simple, let's rerun using the couple again, just to see if it is an influence, if we will again arrive to the same solution that is fully steady, or maybe we are going to find another mode. Okay, so again, let me run here, calculate. And also, just to make it clear, remember that you can also compute a statistic for a steady solution. So enable this one, and then you are going to gather your statistic. Okay, feel free to do that one. For the moment, for the time being, I will disable that one. I will just save some computational resources and calculate. So let's see again. Same question. No. Okay, overwrite everything. And let's wait a little bit. So let's see a couple. Okay, iterating. Okay, so let's see what we have now. We're starting from this condition. Okay, we arrived to a converged solution in testing now. That see that now it was much faster than the previous one. Okay, but see that we have initial transit, and then whatever was happening there was damp very fast. Okay, so as we plot again, see that we have this pretty much is the same. So we don't see any influence in this solver. So our next step, let's do again and go back to this setup simple. Okay, so this is another family of solver. Okay, it's also robust, but generally speaking, they have a slower convergence rate, but the computational overhead is much less than the couple. So you monitor the couple, you will see that couples use a lot of memory. So let's run through using this one. So you can go and you can initialize again, or you can restart from the solution. There is, okay, it's not compulsory to proceed that like I was doing previously, that interpolated. Okay, you can restart from this solution, and actually I will do that. So in this solution, I will add now a perturbation. Okay, so I have that field that is, let's see what we have. Okay, see that the field is perturbated, and starting from here, okay, without initializing from zero, okay, I will go and I will keep computing using a new solver. We're going to see a jump in the residuals, okay, but nothing bad. Okay, we will expect that one. That is something, a normal behavior. And let's see what we have now. Okay, so also pay attention that these are our residual, our quantitative of interest. I'm converting like this, and let's see what we're going to have now. Okay, I press. So we see that jump. And let's see what we have now with this simple family solver. So something that you might notice right away is that the cost per iteration is lower. It's much faster. And as you start to monitor memory, you also will realize that they use memory. And in terms of maybe look at that, we are now seeing some oscillations. Okay, so probably we need to let it run. But see that, for instance, leaf, it's not flattening like the couple. So this is what I want to tell you, that doesn't mean that the couple is wrong or the simple is wrong. Both of them, as they have different numerics, probably the couple, as it putting all those equations together, it will reach that steady state faster, and probably it will reach a solution. Okay, instead in the simple, as segregated solving equations one after the other, it doesn't reach that steady state that the couple is reaching. However, the physics that you are going to see in the segregated, it might mirror better what in reality we're expecting. In reality, we're expecting some vortex shedding. Okay, but in theory, neither of those solvers are wrong or right. Okay, remember in this case we have vortex shedding. So the ideal solver will be on a steady solver. Okay, so we're running this one, getting initial solutions, and we're going to see what happened using different solvers, different initializations that we're going to see. So let's wait a little bit and see how progress the residuals, and then we are going to move into a qualitative post-processing and evaluate the integral length scales and refinement criterion. Okay, so let me stop after 850 iterations, kind of minus the previous one that we had using the couple solver. So just to show you, this behavior is clearly, we have a very different behavior from this that you see here, the one that it was the couple solver. Now the simple is capturing a different physics. So it's just telling this is not wrong, it's just telling you that you have unsteady behavior, okay? So you have the lift and drag forces. And if you visualize here, you will see that you have some shedding. So this is an advice. Sometimes it's can be a good idea. Just first start using quartz mesh in your problem, and then probably switch solver. So the couple is very fast, so run with the couple, and as you get to a solution, then switch to the simple and run few iterations to see if there is some different behavior. Okay, so I will stop this one here. I will save this case again. We'll call it simple now, and I will save another interpolation file. Okay, so see that now we have another interpolation file. It's very different to the one from the couple that we can use in some other meshes and quartz meshes. Call it simple. So now we're going to post-process the integral length scales and the refinement ratios. Just to recall this from the lectures, so we can compute the integral length scale if we are using the RANS models that we have these two quantities available. So we can compute it in this way. Okay, so this one is going to tell you, the largest vortices in your domain and where do you have those, the wake and where things are happening. So see that, for instance, in this case, the Hammett body that we already did, see that you put your integral length scales and you have it there. So this gives you a reference, but however, we have some vortices there. Okay, so also, so the question is my mesh good enough to resolve those vortices? What is there a criterion to determine that? So we have this criterion called the ratio of integral length scales to grid scale. So we relate L0 that we just computed with the dimension of the local cell. Okay, and in generally speaking, if this value is less than 5, we're going to see how to compute it. It means that your mesh still requires more refinement, okay, to resolve those scales in a proper way. So how to compute RL is just this ratio L0 delta, which represents the mesh, okay, grid length scale, and this one will kind of be the smallest cell that edge in your cell. These are sometimes can be a little bit tricky to compute. You have that information available in Fluent, but it's trickier, so you can approximate that like this. In this case, we're taking the cubic root of the cell volume, but you can imagine that you can compute it in any way. So if you have a perfect uniform mesh, this will be a very good approximation. If you have tetra meshes, it might not be very good. So in tetra meshes, you might use the faces, or you can compute some other criteria like the sphere circumscribing that pyramid or triangle. Okay, so there are many criteria. But I have to say that this one works very fine. And remember, after all, at the end, this will be a rough approximation. Okay, so I think this works very fine. So this number RL should be larger than 5. Okay, and ideally something about 10 to resolve well those integral length scale. Okay, so the absolute minimum is 5. Okay, and then everything above 5 is something that you are gaining. Okay, you are gaining more accuracy, better resolution, but we know that you are going to have larger meshes. For accurate length simulations, okay, the integral length scale must be sufficient resolve. Therefore, it's recommended to have a value of 10. Okay, so we're going to work it out. So we have RANS, URANS, and VLES. 3 to 5 is acceptable. Let's put the upper limit, the lowest limit, or the highest limit, let's say in 5 for these simulations. Okay, so what we are computing basically is this. So we're saying that to resolve a vortex, we need at least 5 cells. This pretty much makes sense. You want to resolve it like this, and as you put 10, you will get better resolution. And see that everything is determined, it's something locally, okay, by your cell length. And then the smallest vortex, okay, you will compute it like this. It's L, the smallest scale, and delta will be equal to L half. So to resolve a small one, you will need to put at least 2 cells. Okay, so this will be our criteria, these two, to resolve vortices, the large one and small one. So you see that the more you put, the better your resolution, the finer your mesh. So this is what we have. We're resolving here where energy peaks Remember, also here always we need good resolution, and here we start the energy transfer, boom, up to the smallest scales, and then you will have, let's say, a cutoff grid scale, and from this point here on, you will model everything in scale resolve simulations in runs, everything is being modeled. So from where we get this number of 5 or 10, so first it made sense to say 5, but then there are some also some experimental works and based on DNS. So basically you can construct this plot, the cumulative turbulent kinetic energy against length scales, and you get something like this. So you can say that, for instance, you go here and you say, for instance, if I want to solve 90% of my turbulent kinetic energy spectrum you have here, you will need to have a ratio about 0.16. Okay, so you need to go here. Okay, for instance, you want to get 0.8, you need to have 0.42. So this is cumulative. You are accumulating all your energies. You go closer to the closer that you are to 1, the better your resolution. Okay, so this is based in experiments and DNA simulations. You have some reference here. You go to Pulp and you will have a better explanation, but also there are a few papers that explain this. So basically, look at that. We define L also as delta 2. If you put L here and then you take the reciprocal, you will get this ratio L0 delta. So see that as you put here, to resolve 80%, it's telling you that you need something about 5 cells. But ideally you want to be closer to 10. And from here, from where this number is coming. And see that pretty much is telling you that if you want to resolve just 10% of that spectrum, you will need, well, it's telling you just 1 cell, so it will be too diffusive. Probably unacceptable to resolve integral length scale with 1 cell. It is not acceptable. It's 150. It's telling you that 2. So that's why I'm telling you just to put a limit on 5. That is the absolute minimum if you want good resolution. Okay, which kind of will tell you 80%. So what you are going to get when you plot those quantities is something like that. So if you don't show the values above 5, everything that you see means areas that require refinement. So this is the back step that we did as well. And see that here where you have the recirculation is telling you that you need more refinement. So then when you refine your mesh, see that everything is well resolved. So these areas, okay, will require more refinement, but in general, it's working like this. At the walls, by the way, you will use Y+. This criterion is just good for the core of the flow, okay, where you have those vortices, okay, those larger scales. The smallest scales at the wall where dissipation is happening, you will need to use Y+ or Y star to measure those. So now that we know what are those quantities, let's visualize. So remember that we computed. Let me show you again. Here you have in custom field, let me manage, and we compute L0. See here that we have it here, and then RL, we compute it like this. And those two quantities are available for us. So if you go custom field functions, you will have it there. So see that L0, and here is where you have all your integral length scales, okay, the largest vortices. So it's telling you that I have something very large there. By the way, see that is in this case, using the simple, what we're going to see is that for every iteration we're going to have different behavior. Okay, this is local but also iterative. Every position or different weight configuration that you are going to have different values of L0 and RL. And if I plot RL, it's showing me these values, and see that let me go auto range and let's put the limits from 0 to 5. Click to range means that everything above 5 it will be clipped, means that those regions above 5 are the regions where you have in theory a larger resolution, a good resolution. So the largest vortices, see here, it's telling you that that is okay, but in general this mesh is not okay for this case. It's not resolving properly all your large scales. Okay, so see that probably the much larger, yes, but then this change in time, but this is not okay. What you would like to see is that all this region Is that not visible, meaning that all your work is well resolved. Okay, and if I plot the mesh there, okay, let me go back. I want to plot the mesh, just display. That basically all our problems would be due to this extraction. Okay, so as we increase that extractions, we're going to see now we are going to get a better resolution. So now we have that, and let's do something. We computed for this simple case. Now let's go back to Pimple. Yes, sorry, I was thinking about some other solver. Let's go back to couple, and let's see what happened with the couple now that we have this behavior, and let's see what RL we're going to see. If we go back to that steady behavior, let's see what integral scales and grid refinement ratio we are going to see. So don't do anything, just change to couple and run again. And let's wait a little bit to see what happened here. So in our case, arrived to convergence in a few iterations. So see what happened for a highly unsteady state. Look at that, the couple solver dumps really fast everything. So let me go here, and then we get again the steady solution. So this is the main difference. You will see couples are very efficient. In a few iterations, it will converge to a steady state. Instead, segregated solvers are more sensitive to unsteadiness and sometimes might not converge. And in this case, it doesn't mean that the segregated is wrong. Probably the segregated is giving a more realistic behavior. But in some cases, where you might have a steady solution, the simple will take much longer to get to that solution. So let's plot integral length scales in this case. And auto range. Okay, so we have this. So let's plot first velocity just to see that we have our field as we were having, and then as you go integral length scales, here's where you have the darkest vortex. It seems like kind of an average of the let's say oscillating solution. Now as I put RL auto range, and I want to see from 0 to 5. So in this case, it's telling me that it might be resolving well, but we know that this is oscillating. We don't see the fluctuations here. Okay, we're not seeing any fluctuating quantity. So velocity, so we plot, for instance, in Y, so that we don't have any fluctuation there. Even if you compute the statistic, you will get the RMS, and it will tell you that there are no fluctuations. So this is why it's always a good idea. Couple and then simple. Couple, you reach fast some solution, steady solution, then switch to the simple to see if you can capture some oscillation, if it can trigger some oscillations. So we have the two solutions. We save the two files, okay, the two interpolations that we're going to now to use in a final mesh. So just to show you, so let's open now, you go read case. So if you go instead of quartz folder, you go to find and go to runs, read that case. Okay, so immediately see that this mesh is finer in that direction, spans Y direction, and let's interpolate the solution, okay, the quartz. So as you go interpolate, read, look for your file, whatever you have it. So I have it here in quartz, runs, and let's use the simple, okay, I want to use the simple. And this you plot here. We have the solution, and now using this, we can go and iterate in this new mesh. So let's run first. Now let's start from the simple. Okay, let's go simple. I use this one, and let's run like probably 500 iterations, and let's see what we have now with this new mesh. Okay, so let's do a few iterations. Okay, so after about 360 iterations, 350, look at our residual behaviors. And as you look at CD, look at that we have all the oscillations and the steadiness, and CL, all the signals. Okay, so let's go here. If we plot velocity, okay, we have our plot in the final mesh. And well, remember every now and then just save everything. So call it simple there. So we have a solution there. We can go also and write down the data. Okay, so save this simple. And you can look everything here, no Q criterion. Later we're going to plot no Q criterion, vorticity, everything. But let's take a look at the L0 RL. So this is the study, you know, it's state simulation. They're inexpensive, of course, it's also, so we check everything that we have it working here, that we can pay. We can do many simulations, inexpensive, and then when we move to SRS, we know that we're doing things right. So you are here, see the integral length scales. As you recall, the other, there may be some differences. In the other case, was something much larger. And if I plot RL, I already see some difference in the maximum value, but and see that now this one it's much better. Okay, so see that now here it's telling you that everything is resolved here. There are some areas that might not be working fine, but again, you get the idea that we went to a final mesh and now we have a better resolution. So it might be that probably we might add another refinement level in this region, but look at that what it's telling, because if you have the geometry, you know that this is the region, the critical region, where starting from the mesh that you have. Okay, let me okay, so starting from this mesh, you can start to do some refinements. So see here that maybe it would be better to make another refinement in this direction, in the X direction. The Y seems to be okay. So you see that this criterion is giving you a lot of information. Density is constant. We have pressure also. Okay, deselect there. And see that also an indication of vortices are low pressure area. So you have vortex here. But we know that we have the Q criterion. So let's plot the vertical structures using Q criterion. So that when you go in results, create isosurfaces. Okay, and I want in my domain the Q criterion is located in velocity in Fluent 2020, in older version, I think it is in Turbulence. Choose here Q criterion, create. Okay, let me change now. So it's a positive value there. You are going to play with the range. So in this case, 100 will be okay. So just create another one, and you can visualize there again here contours, and you should have it somewhere here. Okay, Q criterion 30, display, and here you have your vertical structures. Okay, so you can reduce, and you go back here, 30, and let me change from that. Let me go to 10, save compute, and replot, and see that we have the structures there. Okay, so again, this is on a steady version, so we don't see very clearly all the shading like in the presentation, like in here. Okay, so this is fully on a steady. Okay, even we should get something similar to this in the urls. Okay, but this is the first step. You see that it was kind of a very inexpensive. It was inexpensive, and we have an idea of the qualitative mesh. So here, let's conclude something. The quartz mesh is a good one to get the initial condition, okay? But when we put there the criteria that we're using for to assess the goodness of the mesh is not good enough. And then we have the fine mesh that is much better, okay? It can be better, but it's already much better. We see a big improvement, okay? So our next step, that what we have here, we have the interpolation file for quartz and fine. Then we're going to move to the unsteady solver, the urls. Okay, then we're going to capture some time signals. Before stopping here, let's do something also. Let's get the interpolation file for the couple solver and the fine mesh. So you go into methods, change here to couple, and let's launch this one. And again, should be something fast. Okay, but interesting, look at that, the cost per iteration is much higher. You'll realize that probably like 5 or 6 times lower than the simple. Okay, so let's wait for this solution, and then we move to the next part. Okay, so look at behavior of the couple solver. So see that very fast it went to the steady solution, okay? And CLCD stabilize, kind of stabilize about the mean value of the sample, okay? Not necessarily, but it looks like. For instance, here it's quite different. So if we check here the RL, okay, we have pressure. So our interior length scales, and then we go RL and outer range. And as you recall the previous mesh, you will see that this probably it's much better. Okay, the RL limits, let me erase this one. It were up to 8, I will recall, or 10. Look at here that we have larger. Okay, it's telling me that we have much better resolution in many areas. And the integral length scales, well, pretty much the same should be. Okay, so this is our couple solver. So let's write this case also. So we have a starting point here, couple, and let's write also the interpolation file. Okay, so just to summarize this case, we study couple and simple solvers in a quartz mesh. We saved the interpolation file. We saw that the difference. Also, we move to the finer mesh and we interpolate the solution from the quartz to the finer. Okay, so these are basic steps that you will need always to do before running SRS simulations. Okay, then you compute the integral length scale, use the RL criterion to assess the goodness of the mesh. And based on the length scales, then you have some other criteria for the mesh, but this mesh, you can see, saying is hexahedral. Also remember to plot your y plus on the surface. Okay, so in this case we are below, so SRS is also recommended to be below 100. So here in general speaking, it's a very good value. Maybe we have a large percentage in the buffer area, the one that we try to avoid, but let's say that in this case not a problem. So see, that's well resolved on the surface. So as you put 30 to 10. Okay, so you will use the Y plus at the walls and the RL in the core of the flow. Okay, so let me hide a little bit more. Okay, so what we don't see here is above 20, then we have some green. So we have many cells in the 10 to 15, so not very desirable. But wall functions is, so we know what they are doing. Fluent have a robust implementation, but let's say it should be better to have something or below below 10 or above 30. Okay, so if you have your geometry, you have the dimensions, you can get a better mesh. So now let's move to the unstatic case, and that's all for this tutorial.